really good on time, so we're back on schedule now, actually. The next speaker is Stebbins, talking about nearly all skies.
Okay. All right, so this is a artist's conception of sort of a scaled-up version of the Pittsburgh cylinder, which we showed Fermi Lab and Jeff Peterson, Rajat, Lee are interested in this project, and maybe someday it will happen. Okay. So most of you in the audience are probably familiar with optical optical redshift surveys, things like the Stebbins survey, 2DF, and at least for some of them, you get these nice multi-band imaging, three-dimensional images of the sky. Of course, the idea with 21 centimeter is that basically you only have one narrow emission line, which hopefully you can subtract out from the foreground, as we mentioned. So it's not color, it's grayscale. And the nice thing about it is you don't have to, the idea that we're talking about, you don't actually have to pick out the individual galaxies. You measure all the light. So it's like, you just measure all the light on the sky and you know what redshift it is coming from. But that's sort of the big difference between these 21 centimeter density mapping surveys and the typical optical infrared surveys that people have used to map out the large-scale structure. The really nice thing about the 21 centimeter idea is that, generally speaking, for the optical infrared surveys, getting good redshift information is fairly expensive. You have to do a separate spectroscopic survey. Of course, there's the cheaper photometrically approach, which might give you error bars like this for the redshift, the true redshift versus the estimated redshift for a photometric optical survey. And this is what you get for a redshift for a 21 centimeter survey. And the reason you can do that is that you just have to take the signals that you get them in phase, use a FFT, radio frequency spectral analyzer, and you get the frequency out automatically. If you know what the initial frequency is, because there's only one line involved, you map automatically get the redshift. And if you're interested in, say, mapping out the dark energy by looking for these Bayer and acoustic oscillations, this photometric approach greatly limits the number of modes, because you basically have no resolution in radial direction. And anything that approaches really all sky with the photometrics will always be worse than something that has a spectroscopic level of resolution, just because the number of modes is greater. So that's why I think this is a really interesting idea for the future of mapping out the structure of the universe. Of course, the challenging thing is really the fact that the fraction, it's really hard to get high resolution cheaply with a radio telescope, just because of the fraction on it. It's sort of like a history of working with Fermi Lab participation in the large-scale structure effort. With a smaller telescope and a bigger telescope, and maybe the next step would be this much bigger telescope. But fortunately, the cost per unit area for a radio telescope is fairly inexpensive as compared to an optical telescope. I like to sort of characterize this as like a field covered with chicken wire, basically all it is, and then you have this dense array of feeds on the ground. So it's a fairly relatively cheap idea, and we think that this is cheaper than that. Modifying this telescope to do the dark energy survey should cost more than it would cost to do the solar radio telescope. Okay, so the idea is intensity mapping. You don't resolve individual galaxies. You just resolve the large-scale structure. So that's bad. Here's a sort of a slice through, or a little core sample through the D2 survey. You get galaxies, you get the galaxy colors, their types, with all this nice three-dimensional information. With something like the cylinder radio telescope, you just get something like this. Just one line rather than all these points. One interesting thing is that since it's fairly easy to get high spectral resolution, you can actually see voids. Say with a 1 megahertz spectral resolution, you actually should be able to see voids in the galaxy distribution. And this is sort of a simple model of this particular D2 core. Probably I'm including some elliptical galaxies that actually have very little H1 emission. So a lot of these H1 be there. But I think in the frequency regime, you actually may be able to approach the individual galaxies with something like this cylinder radio telescope. Of course, you won't be able to resolve an angle at all, but you will be able to see little peaks in redshift. Okay, so as Ray Lee mentioned, the big problem is the foreground is seen very large. So thousands or hundreds or 1,000 times bigger than the simulator you're looking for. So that sounds like a problem. But as Lee pointed out, the foregrounds are smooth. And that just is a physics argument. There's no way that the foregrounds that I looked before, synchrotron, free emission, and microwave background, can have spikes in frequency dependence. So it's really only a matter of taking the frequency dependence and getting out the high frequency part of that frequency dependence to measure the 21 centimeter emission. That's not necessarily true in the other of the two dimensions, in the angular dimension. Remember, we have two-dimensional mass. There's frequency, which corresponds to radial direction, and angle, which corresponds to the transverse direction. And there's lots of point sources that contribute to the radial emission at the frequencies we're talking about, and they'll have they can have very jagged angular dependence. and so there's a question of how well can we really factorize the frequency and the angular dependence. Like, can the angular dependence leak into something that looks like a frequency dependent thing that might mistake for 21 centimeters? And this is really compounded by the fact that for a given telescope, the angular beam size varies as one of the wavelengths of the frequency we're talking about. You could, of course, spend a lot of money and try to build a different telescope for every frequency and sort of match the beams, but that's really too expensive. You're really stuck with doing one telescope with all the different frequencies, and necessarily sort of your angular resolution will vary with frequency. So that automatically sounds like you're going to mix up the angular and the frequency dependence. And so that's the question I'm mostly going to try to deal with in the next few minutes. So as sort of a toy problem, I'm considering something less like the cylinder radio telescope, which I mentioned before, and something more like the array of dipoles. The particular thing which is computationally fairly easy to do with your laptop in 2 minutes is 8x8 array of dipoles. So it looks a little bit like the MWA here. Okay. So with an array of dipoles, of course, you use the magic interferometry to produce beams with an 8x8 array with spacing of lambda. So for at 1 gigahertz, the spacing needs to be 30 centimeters apart. So it's actually a fairly small telescope. It's a really teeny telescope. You get a beam pattern like this. So this is a synthesized beam pattern, the best angular resolution to do with such a telescope. And notice there's a logarithmic color scale. This might be your main beam, and but you get all these grading side lobes, all these side lobe things, and that's sort of inevitable. Now the reason why you get this funny, so this is what I'm plotting here is the beam versus for at a given time versus right ascension and declination. Of course, the reason why you don't see anything in the lower part is that I'm doing this at a particular latitude. Particular latitude is KBF and you don't see the south at all because the Earth is in the way. But other than that, you basically have some degree of sensitivity to emission throughout the entire part of the spectrum of the horizon. And you get these great side lobes. And because I space the beams lambda spacing apart, not lambda or 2 spacing apart, there's side lobe beams here, but here's the main beam, which actually are just almost as sensitive as the main beam here. So that's an issue that you're going to have to deal with. In reality, your telescope will see almost a large part of the sky, and particularly dipole is the entire sky. Of course, you can synthesize more than this beam. You can synthesize many different beams. In fact, with a simple FFT, you get there's 64 energies, 64 beams. You can actually do twice that with a really complex particle correlation function, which is just running through different beam patterns you can do. And in fact, by varying the phases, you can get a beam to basically be centered at any particular point in the sky you like. But notice that the size of the beam pattern is big. You never get smaller than this particular resolution. It's dictated by the diffraction of it. Okay, so how well can you subtract out the foreground? So here's a model of the foreground of the global sky model by there across the Tankmark and other people. They have this at all frequencies, at fairly high resolution, resolution relevant to what we're looking for the BAO scale. And if you involve with the beam that I showed you before, of course, at a given time you see a given signal. But some people say if you want to map out the sky, you should rotate the telescope. But I say you don't rotate the telescope; you should rotate the Earth. And the thing is, you might think that's expensive, but actually the Earth is already rotating. So you don't have to pay for that. So here's a plot of the time sequence you can scope with sidereal day because the sky temperature is antenna. And as you can see, as different parts of the beam pass through different parts of the sky, there's various things in the black plane that go through different parts of the beam. And some of the wiggles are from the main beam going through a different part of the sky. Some of these wiggles are due to the grading side lobes going through particularly bright parts of the sky. So that sort of makes things complicated. You don't really know where you're pointing at, so to speak. It's not like a radar, like an optical telescope. You pretty much know where you're looking at. Here you're looking at different parts of the sky. But since there's such a large variation in temperature, you don't really know what's happening in a simple way. If you took all 64 beams and you went through the time pattern of temperature as a function of time, you get all these different things. Now the great thing about this is that all these little scan patterns are different things, so they all contain different amounts of information. So can you use all these different scan of temperature, sky temperature versus time to reconstruct the sky? Okay, well you can. Here's a bunch of mathematics. Basically, you can construct a projection operation which takes your sky and projects it into a space of beams. Basically, your telescope isn't sensitive to certain patterns on the sky, and there's certain other patterns on the sky that your telescope is sensitive to. And basically, this operator basically projects onto the patterns on the sky that you are sensitive to. And this is how you reconstruct the map in the limit of no noise or a very long integration time. It's basically the Wiener filter in the limit where the noise goes to zero in the parts of the sky, in the beam patterns that you're measuring. So anyways, this is mathematics. You can look at this later at your convenience. Well, if you take the GSM model and do that reconstruction, you get this. And of course, you don't see the southern part of the sky because that's below the horizon at all times, or at all parts of the day. But you do get this, and it looks sort of like that. And if you do the subtraction of this from that, you get that. So it's smaller. This is the residual map. This residual is actually smaller than that, but you still get large 1 Kelvin, 10 Kelvin things. So you might think this is sort of disappointing. But if you actually look at the angular power spectrum of this, so here's the angular power spectrum. There's L and M. It's not the power spectrum. It's the ALM decomposition. So this sort of corresponds in radio astronomy language to UV coverage sort of. So this is the original ALM, the original angular flow. As you all know, the ALM is from the original image. If I re-image, I get this, and I take the difference, you get this. And what you see is there's this nice region of L and M, or the UV plane, where you actually reconstruct things almost nearly perfectly. the reconstruction very, very well. So that's good news.
This is assuming no noise.
This is assuming no noise. So this is the limit of long integration time. And also another thing that I should mention is this doesn't include the effects of, there might be polarized emission, there will be polarized emission, you have to take that out as well. So conclusions are rotational sensitivity of array of dipoles with good UV coverage, which will overlap at all the relevant frequencies. So I think we are able to factorize angular and frequency structure. Of course, we don't have money to do this yet. We need the money to build telescopes. So another thing you could do with another application is you can build a Photoshop plugin that would do the same thing on any image, which is sort of what this is. And you can be a judge of whether this is a faithful reproduction. Okay, that's all I have to say.
Any questions? Then let's thank the speaker again. And our latest speaker is Rajat talking about local penalization.
Yes, this is another another reionization talk. Yeah, I don't think they hear more about it. Yeah, so before coming to CITA 4 months ago, I was still working with the LOFAR group in the Netherlands. Many of you might not know what LOFAR is, probably most of you do. LOFAR stands for the Low Frequency Array, largest array being built mainly in the Netherlands. Of course, there are many stations also outside the Netherlands, basically in Germany and France, Sweden. So this will have baselines that go from a few meters to about 1,000 kilometers. But the core area, which is important for reionization, will be in the north of the Netherlands, in a small village called Exley. So I'm going to talk about reionization and not too much about the telescope. If time permits, I'll just briefly run through the status of the telescope right now. So I'll just briefly, you've heard a lot about reionization. I don't have to explain this, except the fact that we have to worry. Finally, we are doing some observations soon. We have to worry about what are the major deterrents in our observation. So what could be the showstoppers? Is it the galactic foreground, or is it the ionosphere, or I didn't mention, or is it just RFI that we produce locally? So RFI is a worry in the Netherlands, but it seems to be not so much of a problem as the ionosphere. So when do we need to do reionization? We heard a lot about this. There's a list of things that you can do, but basically, you can come up with whatever it is. Not enough. It's basically, at least just before reionization, it is, if you manage to map out the 21 centimeter, it is probably the best one-to-one, map the dark matter distribution. Right? So you can come up with whatever you want to do with matter distributions in the universe. So this is basically the equation that we are after. It's the brightness temperature that has to be measured. Includes all these different terms. So I always like to look at this in, from two different points of view. One is the cosmology, which hopefully is fixed in some sense. And then it's the astrophysics part of it, right? Which includes all the dirty stuff, all the dirty astrophysics, uncertainties in the astrophysics, radiative transfer, the coupling issues, what the sources are. Some people know what the sources are apparently, but I don't. Of course, if you want to do this accurately, you need something that does ionization, At the same time, you need to do heating, and then you need to do a line radiative transfer for the Lyman after coupling. Lyman after coupling issues are extremely important because the spin temperature there, the way it couples to the kinetic temperature, is basically a function of collisions and a function of the Lyman alpha flux that you have. So Lyman alpha flux is, difficult to obtain at these redshifts because the optical depth of Lyman alpha is very high, and if you want to do a proper radiative transfer, you need to do it in a Monte Carlo sense. And the uncertainties in the OR, all this I just mentioned, there are astrophysical uncertainties listed there. Are the sources stellar, or are they basically mini quasars that do the job? There are schools of thought that sort of favor one or the other. From an observational point of view, maybe quasars are more feasible to detect. But most of them tend to go to a stellar sources being the source of reionization. Apart from that, there are a lot of non-astrophysical uncertainties as well. Galactic photons. I mean, we had last talk that the galactic photons are smooth. Are they smooth enough is the question, because even the RMS, right, the brightness temperature from reionization is expected to be around the 5 to 10 millikelvin range as a photon is much higher, orders of magnitude higher. So to what range can we, to what extent can we actually subtract out the photon, even if you assume that it is very smooth? So what we need is actually a scheme in which we can actually test these different scenarios. So you see, you put in all the uncertainties that you know one by one, and then as a whole, and see how well we can recover your signal. Right? That's basically what you want to do. And to do this, if you want to reconstruct all the astrophysical uncertainties, you cannot do a normal radiative transfer 3D scheme. You need to come up with something which is fast and good enough so that you can explore this parameter space of sources and whatever, right? So to do this, we came up with a very simple scheme. First, we developed the 1D code, and then explore the simplest parameter space, or not the simplest, but the basic parameter space of if the sources are stars and quasars, and for a range of properties of these sources, we actually constructed different models, right? Different radiative transfer problems. So, I mean, the simplest thing is that stars and quasars. This is is like the basic cartoon diagram for that. Right? So UV photons big, no energy. You see, it's a larger cross section. X-rays, smaller cross section. But the electrons just jump out at high speed. So basically, the idea is that it's difficult to absorb X-rays, but once you do, you heat it quite efficiently. So these properties can be sort of folded into this radiative transfer equation, which is coupled to the temperature evolution. And these are very nonlinear stiff equations that need to be solved because these parameters are quite nonlinear if you look at it. This is 1D, right? So if you want to do it in 3D, you have to shoot rays in different directions and solve this for the density profile that you get from the simulation and so on. So what we did, we did a 1D simulation. It's a large reservoir of data if you do a 1D simulation. You can get the ionization profiles. As you see, this is for the quasars. Just changing this, the SED of this and the range of energy that is passed. These are not polynomials, right? But you see that it can cause substantial differences in the ionization. What you're looking at is on the x-axis you have the radial distance away from the source, and the y-axis is the ionization fraction. So on the left, you do not have low energy load. UV photons actually ionize substantially. So on the right you do, therefore you get a larger, bulb. It's all simple stuff. But the heating rates similarly can be obtained. Again, the radius from the source and the temperature. You can do the same thing for the stars, right? Stars on the right side have a different ionization profile, a bit sharper, and also the heating is not that substantial as for the quasars. That's what is in that. And there's some interesting physics. Sometimes you see that the helium ionizing front sort of overshoots the hydrogen This is the interplay between the ability to capture the photon. Helium has a larger cross section, so it might be able to capture high energy photon more efficiently in some regimes. So it's just one thing like that. And this is the observer. So you see that if you have an ideal universe sometime far, far away, and you have one source, right? Everything else is pristine, and there's one quasar that goes off. Its environment is not affected by other sources or ions. What you will see is a beautiful signal because the positive emission sort of saturates. If you look at the equation, it just goes to 1, right? 1 minus TCV over Ts. But the negative, there's no limit basically. It just depends on the temperature of the IGN, which if it's adiabatically cooled, is much lower than the CMB, right? It goes to 1 plus Z squared, where the CMB temperature just goes down 1 plus Z. So you can get a substantially negative brightness temperature. And we are using radio telescopes, interferometers, they don't care if it's positive or negative. You just want to see a contrast. So that would be great, and that would be easily detectable if you want to. But this is the ideal. So, maybe to do a 3D thing. Oh, I'm sorry, no. I can say it. Okay. The idea is that you identify halos in a simulation, right? And then you plug it in. Using these 1D simulations, you just stick in this sort of bubble, assuming symmetry and isotropic ionization all around, right? And then you grow the bubbles in time. You do the proper 1D radiative transfer, and the bubbles will grow according to that. That's why it's a pseudo 3D, because I don't shoot many rays. It's just one ray, so one direction, and I assume that all directions are the same. Which is definitely not true in the universe, because the density in homogeneity is much larger. But in the early universe, I suspect, so that's why it's called a, so why should this approach work? Because we redshift 6 to 12, I assume that it's okay, the universe is more or less homogeneous. It's not true. Let's assume that. And then the over density around the sources, of course, can be corrected for by, some ad hoc scheme. And you can conserve photons because, later at redshift, so this scheme has to work to redshift 6. Never mind, it will not work for redshift 3, 4, you don't care because you want to do reionization. So if the bubbles overlap, you'll be ionizing the overlap region twice. So you can sort of inflate the bubbles sort of in a sense that, to conserve, you can change the volume of the bubbles so that you can conserve the number of photons. So this is the result. What you're looking at here is that the red contours are the ionization bubbles that you get by using a proper radiative transfer code. In this case, it's Crash developed at MBA. Right? And then the blue ones, you can see it's much more sort of roundy. Right? That's this simple approach of sticking in bubbles. And on the right is redshift 6. This is the worst case scenario, right? So if you look at statistics, it's the mean ionization fraction, and you'll see that the errors, this is the errors that are found in the mean and the variance. It goes up to 6% at redshift 6. You can, be the judge of if that's good or bad. But the interesting thing is this: once you have this, again, left is the proper one, right is the simple scheme. You smooth it out using the low part beam, because that's what you're going to see. Because you're not going to resolve more than that. It more or less becomes identical, right? That's the sort of the whole of the way this works. So what you can do is you can come up with entire reionization scenarios in a few hours, right? And it looks, you can have ionization histories of quasar stars. The exact model is not important because you can come up with a model. Give me the models, you put it in the code, and you get whatever reionization history you want in a few hours. So that's the hope, and then you can, of course, do the whole thing, get the brightness temperature, and both brightness temperature to see how the atoms varies and so on. And you can do everything that you do with the normal radiative transfer, right? So the only thing that I've assumed here is that this term is not important. And that's some assumption that most people make in all the simulations, right? All the simulations they do, until very recently, that people have started to realize it's been years ago, but it's only feasible now to do a proper calculation of spin temperature from the laminar flow coupling. Right? This assumption is valid towards the end of reionization because we will build up enough background in the laminar flow. But towards the beginning of reionization, it's very sensitive. You know, if you can couple some regions of space with the laminar flow, that becomes visible, and the rest of it not, and you get this contrast. So it's great if you can do that. So we're trying to see if you can do that. Self-consistency. Yeah, this is just a summary of what I spoke about. Basically, you know, the fact that this kind of semi-numerical scheme sort of works well for most of the reionization system. So perhaps 2 minutes more, then I'll just briefly introduce the telescope. That's LOFAR, and the big, you know, the core area. See, the Netherlands is so small. By the time you put the core area, it fills up potentially. That big plot is the core area, and all the other spots are hopefully. And many of the stations in Germany are already in place, but most of the others are still, you know, under discussion. And mostly, hopefully, within the next couple of years, all the long baselines will come. But as far as reionization is concerned, only that big block is important. That's a 2.5 kilometer sort of core area, which is, you know, we need sensitivity, so it's kind of filled. It has about 25 stations now. So this is the statistics of the stations. There are two sets of antennas that go from 30 to 90 megahertz. Not important for us. Of course, if we could do it, we could go to redshift 30, but we cannot use that anymore. But you go to the high band antenna, 115 to 240, that translates to roughly between 6 and 11.5 in redshift. So that's the redshift range that LOFAR can or should cover. These are the telescopes. Low band on the right. It looks very, I don't know, ugly, right? But it seems to be very effective. So this is the layout of the stations. It's called the Mickey Mouse configuration. The big round sector is the low frequency antennas, and the 2 ears of Mickey Mouse, I think it is called, is the high band antennas. So they are split simply because you will get that extra sort of baseline there. Yeah, so this is doing astronomy. This is how we started, but now it looks like it should be brighter. It looks like that. That's a real station, right? Zeppelin actually took the photograph of that. So it's less than a month when we will officially inaugurate LOFAR and begin observations. We'll wait and see what it does in the next year. Thanks.
Any questions? Okay, let's thank Thomas again.